as I said earlier, that this course ID is PH521. So that is atomic and molecular physics. Okay. So we will be doing mostly basically atomic physics and molecular physics. We'll be covering here, and this is the third semester of you, and you are part of it. So now lecture one, of course. So here, as you see, that this entire slide is about the materials which will be covered in this course. So we'll start with one electron atom. So that is hydrogen atom. Okay. And the Schrodinger equation of that we will be solving explicitly, and that will be kind of, so that is the beginning of our atomic physics course. So we'll be seeing how things work out here, and then from there we'll go on, and then we'll go to a little bit higher or complicated systems. For example, how this one electron atom interact with electromagnetic radiation. So there we'll be seeing this characteristic transition rates, then dipole approximation, and some part. Basically, we are talking about micro level systems, lasers, things like that. So we'll be discussing about Einstein coefficients and selection rules, then spectrum of one electron atoms, line intensities and lifetime of excited states, line shapes and wind. So these are like, I might not follow this exact same order, but these topics will be covered. Okay. So next we'll talk about, like, we discuss fine structure and hyperfine structure. So that is basically how different spectral lines get splitted in different environments. And these different effects will be discussed, like Lamb-Shift, Zeeman effect, Stark effect. So this is, let's say, the basics of atomic physics first part. So this is, I think, somehow you have either covered earlier in your BSc, or let's say in quantum mechanics in your last semester. I think some part you have already covered. Okay. Then we'll go to many electron systems. So here actually we'll be talking about various approximation schemes, like how these systems can be solved exactly and how different properties can be estimated, like center field approximation, then Thomas Fermi model, Hartree-Fock, and let's say self-consistent method we'll be talking. And this LS and JJ coupling I'll be talking beforehand, but this is the exact I have copied from the website. That is why the same order has this kind of here that I've mentioned in the website. But LS and JJ coupling I'll be offering, I'll be discussing before this. Okay, so main electron system will be discussed after LS and JJ coupling. Okay. So then after this thing, center field approximation and the Hartree-Fock, we will be talking about density functional theory. So this is quite a nice topic actually. So specifically people who are working in, I think, with me or even Prakash, I think they will be quite kind of like this will be quite useful for them also, and other people also, like who are working in many different systems, they can also get. I think you have learned quite a lot. I think in the last semester, probably Jobin has covered it. Either Jobin or Prakash, I don't know who took this course. So who took this numerical techniques course? Hello.
So Prakash sir.
Prakash sir. So it was covered already, right? Density functional theory.
Yes, sir. He taught us some.
Okay. Okay. So we'll also be covering this thing, but we'll be seeing how much you have learned in the last semester. But we'll be covering that. And sorry. And then we'll be talking about yeah, and then interaction of electron system with electromagnetic radiation. So this is roughly, let's say, atomic physics will be done here, and after that we'll be going into molecular physics. Okay. So yeah, the second part. So you see, basically this is a very big syllabus actually, but we have to see that if we can cover everything. For example, this molecular spectra itself is a full semester long course. In chemistry department, many people just offer this course. And people, I think, who are working with Manas or even Dantam, they will be seeing more of this, like how big this topic is. Okay. And also this density functional theory, this part is also like one full semester of course. So there are many things which I have to cover in few lectures. Okay. So I'll be trying to focus on only the interesting parts that are relevant for you. Okay. So in the molecular spectra, this is the molecular structure. Then we'll discuss Born-Oppenheimer approximation and the different types of spectra. For example, like rotational spectra, vibrational spectra, and then electronic spectra, things like that. And I think this last part is control principle. So that is the basic part of it. So these parts will be mostly discussed towards the end of, let's say, semester. So let's say last part of let's say before. So if we split it into 4 parts, like let's say 4-month semester, so it will be in the 4th month probably we'll be covering this one. Okay, so it is basically towards the end. Okay, so any question on this so far? Anyone? Okay, good. So if not, then I'll come back to this part. So these are textbooks which will be used here. So the primary book which I will be covering, at least for the first part, will be this book, Physics of Atoms and Molecules, that is by Brunson and Joachim. Okay, so you can, if you want, you can actually get this book online also. You can search it, or sorry, if you want, you can buy it also. So this will cost you, I think, more than like around 1,000 rupees or something, 1,1100. Okay. And there is another book which actually I have studied during my undergraduate days. So people who are from Calcutta University, they can actually relate it to. So this book, S.N. Ghosal. So this is a fantastic book for atomic physics. Like it gives a complete understanding also. So this is a very good book also. So next one is so this is volume 1 and volume 2. Okay. So I will not be covering, I mean, following this book exactly, but some parts like here and there I will be covering. So for first, actually, what the atomic spectra part, I will be mostly focusing on this book, Brunson and Joachim, and this book by Griffiths, basically quantum mechanics, which I think you all have. Okay. So this is again a fantastic book, a very nice book actually. I actually didn't study this book during my undergraduate days, but then when I start taking this course, I started looking into this book, and then I saw that this is a very nice book actually. Okay. So I think some of you have already read this book in last semester, so you will be benefited from that. And then there is quantum chemistry book. So this is by Levine. So this is again a very nice book, and this some part of hydrogen spectra I will be taking from there. And then this is this book by Atkins and Friedman, Molecular Quantum Mechanics. So this will I will also be covering little bit whenever required. Okay. So primary textbook will be this one, Franchen. Okay. And some part will be taken from this one, but these are all reference. The other three are reference books. Okay. So you can choose whichever you prefer to read. Okay. And most of these materials are also available on web, legally or illegally. You have to look for, and then if you want, you can actually find them. Okay. Okay, so there is actually one more book which I didn't mention here. So for molecular spectra, there will be a book on Banwell. Okay, so this is a very thin book. I think it, you can buy it from Amazon or Flipkart. I think it will cost you like around 200 rupees. So this is a really nice book. Like it's very basic, elaborative, and basically it covers lots of interesting aspects of molecular spectra, and like there are lots of useful examples, things like that. So you can also consult that book. Okay, for molecular spectra. So, so this book is by Banwell. So I'll just write it down here. Okay. So this is okay. So this is the name of the book. Okay. So now coming back to this part again. So any questions so far? Any question? No. Okay.
Sir, can you repeat again which books are you mainly gonna follow?
So this first one and the third one.
Okay.
So I will be taking help from these three also, but textbook will be this one primarily. Okay, this Brunson and Griffiths. Okay.
Okay, sir.
Okay. So now I'll do some recap before getting into the actual topic. So as you see, the atomic physics is basically completely built upon quantum mechanics. Okay. So we will be seeing basically we'll be using quantum mechanics here. So the basics of quantum mechanics, it starts with Schrodinger equation. Okay, so here as you see that this is the Schrodinger equation, that is I cross del psi del t will be minus h square by 2m del psi del s square plus b psi. So that is one-dimensional Schrodinger equation. What you do is that we solve it, we find the wave function. So if we know the exact form of b, then we can solve and we can find the wave function. And once we have the wave function, we can have basically all the informations about the system. Okay. Now there is this quantity which is psi square dx. So that tells us about the probability of finding a particle between a certain volume or certain distance at a given time t. Okay. And if you normalize it, that will be 1. That means the total probability that is integrated over this space is 1. Okay. Wait, give me 1 second. Okay. So now let's say if we want to know the expectation value of a quantity, then what we have to do is that we have to take the quantity of which we want, let's say, measure the expectation value, and then all you have to do is that you have to integrate over this like psi over the entire volume. Okay, and in general there is this definition. So I hope this part you already know, right? Anyone has any question on this part? No? Okay. So I'm assuming that you need to answer. You should not be like completely silent. Okay, otherwise I'll know whether you are present there or not. Okay. Hello, am I audible by the way?
Yes,
Yes,
sir, it's
sir.
clear.
Yes, sir.
Yes,
You are
sir.
audible.
Okay. Okay, good. Okay. So next, that once you know what is psi, then these problems I think you have addressed. So that is exactly solvable problems. Several problems they have done. You can solve the Schrodinger equation exactly. So the first one is infinite spiral potential. So here your V is 0 here, and if you solve this equation, you get this kind of wave function, which is basically plane wave. Okay. So sine nx by a, and then the energy eigenvalues will go as 1 over s square. So different quantum number, for that you will get different states. So ground state, first excited state, second excited state, all this thing, and you can see that there are different modes that will be appearing at different lengths, okay, distances. Okay. So that you have already solved, and this will have basically remarkable use in molecular spectrum. Okay, this simple concept. That, so tell me, what is the most useful information you learned from this problem? Anyone?
Some energy is quantized, I think.
Okay, anything else? Anyone? So whom of you have got A in quantum mechanics? Okay. So let me check in another way. So who has the highest CGPA?
Sir, Mohit.
Mohit.
Yes, sir.
Mohit, tell me.
Maybe, sir, the energy is discrete levels. Discrete level of energies.
Is that the only information? I mean, that is the basics of quantum mechanics, that energy is continuous in classical mechanics. In quantum mechanics, energy will be discrete.
Yes,
That is
sir.
the very basic information. Anything else specific to this problem?
No, sir, I'm not getting now.
Okay, anyone else?
So maybe it's only one particle in box.
But that is specific, I mean, that is the definition of the problem. I'm saying what to learn from.
One particle system, it is only not more than one particle.
No, but what I'm saying is that that is the definition, like you are defining the problem in that way. So that is at your side. But my question is, what do you learn from here? What is the most useful information that you get from the result?
The particle never have zero energy.
What has zero energy? Can you repeat it? Hello?
Sir,
Hello.
Yes.
So maybe I think she wants to say particle does not have zero energy in ground state. Like even in ground state, if a particle is in ground state, the particle has some energy, but it's never zero.
Okay. Okay, that is
And
useful information. Yes.
and the energy is proportional to the n square, which is the state of a
Okay.
particle.
Okay. Good. Okay. Okay. Anything else?
So if we talk about this problem, we can also say that for the ground state, the probability of finding the particle is maximum in the center, and the probability of finding the particle at the boundaries is like 0.
Okay, that is also good. But I was talking about something more general. Okay, so you have
Uh,
probably missed it. Tell me.
Hello. So
Yes.
we can conclude that a particle cannot stay at high potential regions.
Where is the high potential region?
Like the boundaries, we always find that the probability of
Okay.
finding the particle is 0.
But that is infinite potential. So of course your particle cannot go there. I mean, if I put you in a jail, okay, and the boundaries of the jail is infinitely long, do you think you can go to the other side? You understood what I'm saying, right?
Yes, sir.
So that is fundamentally impossible because infinite potential, right? If it's finite, then still there might be some probability. Okay, so see, one use information which I actually wanted to hear from you guys, that is, you look at the denominator here in this expression. Okay, En, what is the quantity here in the denominator?
2m.
Can you see it? And then after that,
2m
square.
a square, right? What is A?
Sir, the length of the box or the well.
Size of the box. Okay, so what is the dependence between E and A?
It's inversely proportional to the square.
Inversely, yes, inversely proportional to the square of the length. Okay, so what does that tell you?
Sir, sir.
Tell me.
Yes, sir. So if we keep increasing the width of this well, so we can see that the discretization in energy keeps decreasing, and if A becomes kind of infinite, that is a free particle, there is no discrete energy.
That is not the point. I mean, this is not completely untrue, but this is not exactly true also. Okay. You see, it says that, let's say for a particular n, okay, if I reduce A, that means my E will increase, right? And if I increase A, my E will, let's say, go down, right? Okay. Is that, I mean, do you agree with that?
Yes, sir.
Okay. So now let's say if I talk about two subsequent levels, let's say n and n plus 1. Okay. And if you calculate the energy difference between these two, then you can see that will also go as 1 over s square. Okay. Now, what does that tell you? So let's say I have discrete energy levels here, here, here. Okay. So unfortunately, my tab is not working with this laptop. Otherwise, I would have showed you actually. So let's say I have like some levels which are. So let me try to see if I can get some basically themes and some box. Where are these things? Okay. So let's say I have certain energy level here. Okay, it's not coming out of it. I think I'll better speak. Okay, so let's say I have certain energy level and the energy level above that. Okay, now the difference between those two energy levels, it will increase if I reduce it, which means that the energy gap between subsequent energy levels will increase if I reduce the size of the box. Now, let's say if we talk about a physical system, quantum mechanical system, so something like a quantum dot. Okay, so there what will happen is that there is some energy gap that determines, let's say, what sort of spectra or what sort of color you are getting. Okay, So if we are decreasing the size of the box, that means that we are increasing the order of confinement. So it's basically higher order of confinement. Okay, which means that the separation between energy levels will be higher, which means that if you want to excite, then you have to provide higher energy. But if you want to de-excite, then it will give you a radiation which also have a smaller wavelength. Is this clear? Anyone?
Yes, sir.
Okay. So you will see this concept, you will be useful in many cases. So this energy is inversely proportional to the length square. So that is a very useful concept which will be used and you can actually think of. So I'll give you a very, let's say, example which is not exactly quantum mechanical example, but you can have some comparison with it so that you can remember. Okay. So let me give you an example. Okay. So let's say you are the particle. Okay. And I confine you in one room. Okay, right. Now let's say if the size of the room I keep on reducing, then what will happen? At one point you will see you will have very little space to move, right? Which means that you will feel, let's say, not so happy. Okay, and you will have, let's say, more disturbances. So you will feel like, oh, how can I move? Like this side I want to move, I hit one wall. That side I want to move, I'm touching something else. Okay. So you will be, let's say, very unhappy and let's say kind of not very much satisfied. Now if I increase the size of the room, which means that the walls I am moving away from you more and more, which means that size of the room is increasing, or let's say in this case the boundaries are increasing, you will have more space. Mentally, how you will feel? You feel like you are more happy. Okay, you are stabilizing more. So the disturbances, or let's say the whatever, like bad vibes that you had, now they will be slowly kind of reduced. Okay. Now, if we come back to this quantum mechanical concept here, so if I am reducing the size of the box, that means I have to cost. So basically, the kinetic energy is there. So kinetic energy will increase in that way. Okay. And if I am, let's say, increasing the size of the box, that means I am helping the particle to stabilize because it will have a longer wavelength excitation that is possible. Okay. Does it make sense?
Yes, sir.
Yes.
Okay, chalo. So you actually need to think of these things from this point of view, so that you actually, unless you can connect a potential problem to a physical example, it will be difficult to remember them. Okay, so the next one is finite spiral. So this one you have solved actually. So here you see this is the V naught, which is the height of the potential. This is the attractive potential, and here you can see this transmission probability. It has some sort of kind of oscillation, and it can reach the maximum value of 1. And we have solved this thing. So I think this one you have also seen some practical example probably. I don't remember exactly which example are solved, but this one definitely have solved. Okay. And the next one, which is very popular, that is simple harmonic oscillator. Okay. So here you have a harmonic potential. So what is the harmonic potential? Anyone? Any idea? So you see this potential here that is represented by this dotted line. Okay. Harmonic in the sense that it will have some minimum. Okay. So it is U-shaped. Okay. That means that the center of this thing is the minimum. And harmonic means that whatever little disturbance you can create around this, it will be symmetric around this minimum position. Okay. So if it is, let's say, half k x square, that is the Vx is half k x square, that means it is centered around x equal to 0. Okay. So if you are disturbing this, then it will have an oscillation around x equal to 0, let's say plus x and minus x. So between plus x and minus x, it will keep on oscillating. Okay. So that is called as harmonic oscillation. Okay. But now, if I add something which is, let's say, one term like this, like x minus x, then what will happen is that I will bring in anharmonicity, which means that this potential will not be symmetric around x equal to x0 anymore. Okay. So one side will be a little bit asymmetric or more compared to the other side. Okay. So that is anharmonicity. Now here, for the case of this simple harmonic oscillator, we have a potential which is approximated roughly by this x minus x naught square, and you have solved it, I think, with this rising and lowering operator. Okay, and you have seen this solution that is basically harmonic polynomials and different energy levels that are quantized. So every time you use an let's say a plus, you are going into an energy level which is plus h bar omega above this. Okay, so that way you can rise, or you can also reduce this if you use a minus. Okay, and the energy eigenvalues, it follows this simple formula n plus half h bar omega. Okay, so here omega is the one which basically determines what frequency or let's say what is the nature of the potential. Okay. So because it is related to the string constant k, so k, if k is stronger, that means omega will be higher, things like that. Okay. So this is also another interesting problem which will be used quite a lot in your spectra, molecular spectra, atomic spectra. Okay. So I hope this part is quite clear, and I think this one electron I'll talk later. And so now, so far, any question on this?
Sir, hello sir. Sir, can you please repeat the n harmonicity thing when you said that?
Okay, very good. Okay. So you see here. Okay, let me see if my this tab is working. I don't think so. It is working. Okay. So let's say if I have a potential like this. Okay. So my handwriting is not very good. But let's say this is my x. Okay, and this is my Vx. Okay, so here you can see that this right hand side and left hand side are not exactly symmetric, right? Or let's say in the very simple term, let's say if I draw a line here, so this area here is not exactly same with the area that is here, right?
Yes, sir.
Right. So what does this mean? Let's say when I talk about, let's say the, so let's say this is, see if this works. Okay. Okay. So let's say if this is my potential, Vx equal to okay, so can you see the potential? Right?
Yes.
Okay. So if I have this potential, let's I think write this one x minus x naught. Okay. So let's say this is my potential. Okay. So in that case, what I'll get is that this side and that side both will be symmetric, right? So it will be U separate, right?
Yes. Yes.
So in this case, the force that will be working will be F equal to minus kx, right? Huh?
Yes, sir.
Okay, but let's say if my force is not this, okay, something else. Okay, so let's say if my F is, let's say F equals minus kx plus, I don't know, kx square. Okay, so in that case, my kx plus kx square. Okay, so let's just say that okay, so if my force is not exactly minus kx, but let's say some other term, okay, which is higher order than x, okay, then what will happen is that my V will also take a form that is other than this. So here, let's say if I copy and paste it, then basically I will have a potential which will probably be like, let's say, another term that will be something like, let's say, a cube term. Okay, you understood what I'm saying?
Yes, sir.
So in that case, you see this x minus x naught square is symmetric around x equal to 0, right? X equal to x0. But this cube term is not symmetric, right? So it will be, let's say, like give positive contribution towards one side and negative contribution to other side, right? So in that case, my potential will be asymmetric around x equal to x0, which means that the motion will also be anharmonic. So
yes, sir, yes.
If I'm simply talking about, let's say, harmonic oscillator, that means that here basically I am, let's say, either going, I mean, let's say this is my central position, okay? So it will be moving, let's say this is my 0, okay? So this is, let's say, x, okay, simply x, okay? And let's say this is my minus x, okay? But so this is harmonicity, okay, which means that it will exactly move by the same amount on both sides of the equilibrium. But if it is anharmonic, then it will probably move little bit higher on this side and maybe little bit less on this side. Okay, so it will not be symmetric around this point anymore. Okay, is that clear?
Yes, it's clear.
Yeah. So any question? Anything else on this? Okay, so if not, then okay. So in the next class, we'll, so please do some recap or read this thing a little bit into details, because we'll be requiring this concept. But it looks like you guys need some brushing up. Okay.